Okay, so today we're going to talk about Chapter 1, Part 6, which is function operations and composition of functions. And there's just one definition for this section. So that is the composition. So that is when you use a function as the input for a second function. And it looks like this. F of g of x equals f evaluated at g of x. So I plug one equation or one function in as the input to a second function. It's called composition. Okay, so operations with functions. We're going to have addition, subtraction, multiplication, and division. So the sum of two functions works very much like you'd expect it to. You see that here. Difference, product the same way. Quotient is the only one that has some weirdness, and that is that once you find the quotient of two functions, the denominator function must never equal 0. So it's an additional domain constraint in some cases. Okay, so given the following, f of x equals x squared minus 2x, and g of x equals 3x minus 4, find the function and domain for f plus g of x. Notice h is kind of a red herring here. We don't use that. Okay, so f plus g of x equals f of x plus g of x, which in this case is x squared minus 2x plus 3x minus 4. So all I have to do here is drop the parentheses and combine like terms. I've only got one squared term. I've got two single powers of x, minus 2 and plus 3. So that's plus 1 and then minus 4. There are no domain constraints for any of these functions. So the domain is going to be x is a real number. So in other words, any number you can think of as long as it doesn't include the imaginary unit. So here we're tasked with f minus h of x. So we're going to do f minus h of x, which is f of x minus h of x, which is going to be x squared minus 2x minus negative 2x squared plus 1. Be careful with the parentheses here. They're a lot more important than the previous problem because we're subtracting the entirety of h of x. So if you didn't do it this way, it would be a sign error. You didn't have it in parentheses and the subtraction symbol outside of it. So now we're going to keep, change to make our lives easier. So when we subtract a polynomial, this is one way to do it. And now we can just combine like terms. So x squared and 2x squared will combine to make 3x squared minus 2x minus 1. Once again, the domain is all real numbers. Okay, moving on. So here we're given the task of finding f times g. Notice the closed dot, not the open dot. The open dot is composition. Closed dot is multiplication. So f times g of x is f of x times g of x. So that's going to be x squared minus 2x times 3x minus 4. So we can do this with FOIL. First times first is going to be 3x cubed plus outer times outer is going to be negative 4x squared plus inner times inner is going to be negative 6x squared. And then plus last times last is going to be 8x. So combining like terms here, those two middle terms, 3x cubed minus 10x squared plus 8x. And once again, no domain constraints anywhere to be found. So x such that equations with functions. So once again, we're going to use f, g, and h, but in this case, h and f are the quotient values. So h over f of x. So h of x over f of x, and remember that f of x can never equal 0 now. Okay, so these are generally pretty simple because there's not a lot of simplification to be done. This is negative 2x squared plus 1 over x squared minus 2x. And these don't share any factors. There's nothing to cancel out. There's no real simplification to be done. But I do need to figure out x squared minus 2x can never be equal to 0. So if I find the zeros for that function, it's going to be x times x minus 2. So x could never equal 0, and then x could never equal positive 2. So here's our function. Here's our domain constraints. Okay, so here's a task for you. Find f plus g, f minus g, f times g, and f divided by g of x for the following f and g of x. So pause the video, do that, and then come back and see if you got it right. And it also asks for the domains. Okay, so let's do it. First of all, f plus g of x. Remember that's f of x plus g of x, which in this case is x squared plus x plus x minus 3. Just combine like terms. X squared plus 2x minus 3. And then f minus g of x is going to be f of x minus g of x. And so in this case, x squared plus x minus x minus 3. We're going to do that extra step where we keep change, and then we'll combine our like terms. Yeah, that's the x's will cancel, x and negative x. Now the multiplication. So f times g of x equals f of x times g of x. And so that's x squared plus x times x minus 3. FOIL again is a good strategy. First times first, x cubed, plus outer times outer, minus 3x squared, plus inner times inner, x squared, plus last times last, minus 3x. Combining like terms, x cubed minus 2x squared minus 3x. And there's no domain constraints here. And in fact, in any of them. So in every case, so far, it's been a domain of x is a real number. They had asked for that on all these. So in every case, x is a real number. Finally, we're asked to find f divided by g of x. So that's going to equal f of x over g of x. And remember that g of x can't be 0. And that was the last of the tasks here. So that's going to be x squared plus x divided by x minus 3. And x minus 3 can never equal 0, which means x could never equal 3. So here's our answer. Here's our domain constraint in that case. All right, composition of functions. So when I compose two functions, this is just sort of a little overview of the mechanism. So the input is going to go into the first function, g of x, and then it's going to spit out an output. And then that output is going to go into the function f of x, and it's going to map that to its own range. It's kind of complicated in this visual, but in operation, it's not that different from a regular function. So given f of x equals 2x squared minus 1 and g of x equals x plus 3, find f of g, notice the open dot, of x. So this is often called fog of x, but f of g of x. So that's f evaluated at g of x. So that's going to be f of x plus 3, which is going to be 2 times x plus 3 squared minus 1. So I found the expression that g of x was equal to, plugged it into f, and then everywhere there was an x in f, I replaced with x plus 3. So that's going to be 2 times, and remember, it's a little shortcut here. A plus b squared is equal to a squared plus 2ab plus b squared. So we can use that as a little shortcut, and that's x squared plus 6x. So 2 times 3 times x is 6x plus 9 minus 1. Save us a little trouble to use that shortcut in this case. So that's 2x squared plus 12x plus 18 minus 1, or 2x squared plus 12x plus 17. So there's f of g of x. All right. So here they asked us to find g of f of x. They will not be the same. This operation is not commutative. So I can't switch the order and get the same result. It will be different. So this is g evaluated at f of x. And the same process would apply. This is g of 2x squared minus 1. And so this is 2x squared minus 1 plus 3. And so that's 2x squared plus 2. Much easier in this direction. And then C, f of g of 2. Well, we know f of g is 2x squared, is 2x squared plus 12x plus 17. So 2x squared plus 12x plus 17. So that's f of g of x. And if we find f of g of 2, we can just plug it in here. And so that's 2 times 4 plus 24 plus 17. 8 plus 24 plus 17. 32 plus 17. 49. Now, I think the way they wanted you to do it here was to plug 2 into g. So that's g of 2 equals 5. And then you plug 5 in here. And you're going to get f of 5 equals 2 times 5 squared minus 1, which is 2 times 25 minus 1, which is 50 minus 1, or 49. So the same result can be found by using that diagram method. But I find the first way I did it to be make a little more sense to me. Okay, here's one for you. Pause the video, work this out, come back and see if you got it right. Okay, so find f of g, g of f, and then f of g of 3. So first, f of g of x is f evaluated at g of x, which is f evaluated at 4 plus x squared, which is 2 times 4 plus x squared minus 3. And so that's 2 times 4 is 8 plus 2x squared minus 3. 8 minus 3 is 5. So let's write it 2x squared plus 5. Usually you go in descending order of the degree. So in other words, you start with the highest degree term and we go downward. So the way they had it written here is unconventional. Okay, now g of f of x is g evaluated at f of x. And so that's g evaluated at 2x minus 3. And so that is 4 plus 2x minus 3 squared. Okay, so 4 plus, and then we can use our little shortcut again if you like. It's a little more complicated here, but 2x quantity squared is 4x squared. And then minus 2 times 2x times 3. So that would be minus 12x. So 2 times 2 is 4, 4 times 3 is 12. Positive times a negative is negative. So minus 2ab in this case would be minus 12x, and then plus 9. So once again, this uses a shortcut. And just to help you remember that a minus b squared equals a squared minus 2ab plus b squared. So that's the shortcut I used here. Okay, so adding 4 to 9, I get 4x squared minus 12x plus 13. So that is g of f. Up here's f of g. F of g is important to us because we're going to use it for this next part. So they want f of g of 3. So I plug 3 into this. So I can do it that way. I'll do it this way. F of g evaluated at 3. So if I plug 3 into g, 4 plus 3 squared, that's 13. So 4 plus 9 is 13. So that's f of 13. Remember that f is 2 times x minus 3. So this is 2 times 13 minus 3. So that's 26 minus 3, or 23. Okay. So here we're asked to find a composite function with a restricted domain. So when we find f of g of x, first of all, we have to find g of x. So any domain constraints for g will be considered at this point. There are none. G has all real numbers. So the domain for g is all real numbers. It gives us no problem. But when we plug it into f, we do have a problem because the domain here is going to be x minus 1 is greater than or equal to 0, which means x is greater than or equal to 1. So we can only consider g of x values where the output is greater than or equal to 1. So I'm concerned only with places where this output is greater than or equal to 1. So if I think about the graph x minus 1 squared, so anything less than 1, and I'll graph y equals 1 here. So everything below that line, which looks to be between 0 and 2, is a problem. So if I hit trace, and let's actually zoom in a little bit. Let's go from -1 to 3 and -1 to 3 here. I think that's going to give us a real close-up of that relevant portion. So yeah, between 0 and 2, we've got values of this function below +1, which are going to violate the input rules for f. So I cannot use anything, an x value of g, between 0 and 2, but the bounds will be included. So it's going to have to be the case, and this is just analyzing for the domain here. It's going to have to be the case that x is less than or equal to 0 or x x is greater than or equal to 2. So that's going to be the domain we'll have to use for g of x in order to get outputs that make f of x valid. So f of g of x would have this for its domain. Now let's find the actual expression. So that's going to be f evaluated at x minus 1 squared. And that's going to be the square root of x minus 1 squared minus 1. And it would be unusual to leave it in this format. So I'll go ahead and expand that. That's x squared minus 2x plus 1 minus 1. And so I have, if I can bind my like terms, the ones cancel, x squared minus 2x under a root. So there's f of g of x. And here is the domain we'll have to use for f of g of x. Okay, now for part B of this example, once again, we'll have some domain restrictions to consider. Find f of g. So first of all, we have to find g, and g has some constraints here. So x squared minus 1 has to be greater than or equal to 0. In other words, x squared has to be greater than or equal to positive 1. So x squared is greater than or equal to positive 1. Again, if you think about that graph of x squared, if I were to draw a line at positive 1, you would see that between negative 1 and 1, it was below. So the constraint we have to use here is x is less than or equal to negative 1, or x is greater than or equal to positive 1. Those are going to make this g of x valid, have a real result. But once we plug it into f of x, it must also be the case that it's not 0. So that's going to get rid of the or equal to part here. Because if I had negative 1 squared at positive 1, 1 minus 1 is 0. So that's where we would have a problem. So if I get rid of the or equal to part, it will satisfy both the needs of g of x, which are to have a non-negative under the root, and f of x, and that is that you cannot divide by 0. So the division by 0 is going to preclude the equal to part here. So x less than negative 1 or x greater than 1. That will be our domain for f of g of x. Now let's find it. So that's going to be f evaluated at the square root of x squared minus 1. And so that's going to be 1 over the square root of x squared minus 1. So there's our f of g of x, and here is its domain. All right. Interesting problem. Here's one for you. Give me the domain, find f of g, pause the video, and then come back and see if you got it right. All right, so let's see here. First of all, everything we find has to be valid for this. This has no domain constraints, so that's not a concern. However, it is in the denominator of f of x, so g of x will have to be not 0. So we will have to have this to be true. In other words, x squared will never equal 1, so x could never equal plus or minus the square root of 1. X could never equal negative 1 or 1. Now let's find f of g. So here's the domain. So that's f evaluated at g of x. And so that's f of x squared minus 1. so that is 3 over x squared minus 1. So there's the function. Again, the domain is x cannot equal -1 or 1. Okay, so decomposing a composite function. So here they task us with finding a set of functions, f and g, that would compose to make this. So I want f of g of x to equal 1 over x plus 2 squared. And they say don't use the identity function because that would be too easy. All right, so if I let f of x equal 1 over x and g of x equal x plus 2 quantity squared, that would do it. There are many different answers you might give, but this is the obvious one. Part B here, same type of problem, and they give us, I'm sorry, that's the same problem. All right, here we go, part B. So here we have 3x squared minus 12x plus 12. We want an f and g that compose to make that. A little more challenging here. There will be no obvious answer here. Everybody would probably have a slightly different take on this if left to their own devices. Here's what occurs to me. If I let f of x equal 3x squared minus 12x, I'm sorry, I should do that the other way around. Okay, so if I let this one be x plus 12 and g of x equal 3x squared minus 12x, then it would compose to make this. But again, many different answers are possible. This is one that would be difficult to have a specific answer that a bunch of different people would arrive at independently. So here's one for you. See if you can figure this out. Pause the video. Come back and see if you were right. Okay, so once again, you could have a couple different answers. Here's the one that occurs to me. If I have f of g of x equals the square root of x minus 1 over 3, then I should say f of x equals x over 3 and g of x equals the square root of x minus 1. That is sort of an obvious answer in this case. All right, so we'll forego this last example in this case. And I'd like for you guys by the due date to complete page 61, 2 through 28 even, and 29. So also 29. See you next time.